The 850 millibar level generally exists at about 4 to 5,000 feet, or just over 1 kilometer above mean sea level. Depending on the location, the 850 millibar level may actually be underground. This occurs in a lot of high altitude locations, such as a place like Denver. As with every upper air map, there's a standard set of conventions used when analyzing an 850 millibar map by hand. Geopotential height contours, isoheights or isohypses, are drawn in solid black every 30 meters, or 3 decameters, with a base value of 1500 meters, 150 decameters. So you draw in 1470 meters, 1440 meters, 1530 meters, 1560 meters, and so on. Isotherms, or lines of equal temperature, are drawn as dashed red lines every 5 degrees Celsius, although intervals of 2 or 4 degrees Celsius are acceptable as well. Everything else is at the forecaster's discretion. Often isodrosotherms, or lines of equal dew point, are drawn in using the same conventions as isotherms, and isotachs are common as well. Really, whatever's helpful to the forecaster is just fine, but those are the main conventions that are used when manually analyzing an 850 millibar map. So the main feature that we look for when analyzing an 850 millibar map, especially in severe weather scenarios, is the low-level jet. That layer of enhanced winds in the low levels of the atmosphere centered around the 850 millibar level, generally with some sort of southerly component, that can assist a severe weather setup in a couple of ways. Number one, it acts as a mechanism to transport low-level moisture into a region to make the air mass juicier and more unstable. And number two, it can help to increase low-level shear and enlarge low-level photographs to support a robust tornado threat. The low-level jet is a semi-permanent feature across the plains that tends to increase during the nighttime hours and decrease during the day due to changes in the pressure gradient based on the heating and cooling of higher and lower elevation areas. During the nighttime hours, the higher terrain to the west cools much more quickly than the lower elevations to the east. This induces a strengthening pressure gradient, and because the pressure gradient modulates the speed of the winds strengthen over the plains at night. And the Coriolis force, which is related to the turning of the Earth, turns those winds to be out of the south, and that is how you get a strengthening of the southerly low-level jet during the nighttime hours. The low-level jet is also often enhanced in the warm sector of low-level cyclones, which we can easily identify on 850 millibar maps as well. In general, we're looking for 850 millibar wind speeds in excess of about 30 knots when pinpointing the areas with the most robust low-level jet, and those winds will generally have a significant southerly component. So for example, on this 850 millibar map here, we can easily identify the low-level cyclone, which is very deep and is centered over eastern Kansas. Out to the east, which is where the warm sector is located, we see a large plume of 40 to 45 knots of generally southerly flow extending from the Gulf Coast states into the Mid-South and Midwest. That is our low-level jet of greatest concern for severe weather potential. Technically, we could call this plume of stronger flow on the backside of the cyclone a low-level jet, but that would not be of importance in severe weather forecasting. On most model sites, as well as the SPC mesoanalysis page, isotachs will be color-filled so that you can easily pick out the low-level jet. For example, on the College of DuPage website, which I have an example of here, the yellow colors represent at least 30 knots of flow, and the red colors represent at least 50 knots of flow at 850 millibars. Also, by standard convention, if you're analyzing an 850 millibar map on your own, the axis of the low-level jet should be denoted by a big red arrow pointing in the direction of the flow, but this is not a necessity. Oftentimes, you can easily identify low-level jets through isotach analysis. Related to the low-level jet, we can also use the 850 millibar map to look for areas of low-level temperature advection. Just as a refresher, advection refers to the transport of a quantity from one region into another, so temperature advection is simply the transport of warm or cold air from one region to another. We can identify areas of temperature advection on the 850 millibar map by looking for areas where the isotherms, the lines of equal temperature, cross the geopotential height contours or isoheights at any angle, with the areas of greatest advection occurring where the isotherms are perpendicular to the height contours. Advection can also increase when the isotherms are packed more closely together, signifying a very strong temperature gradient, and or when the height contours are packed more closely together, which signifies a stronger height gradient and thus a stronger wind to advect an air mass into a region.
Storm chasing is already tough. Dixie Alley makes it tougher. Free ebook link in description.
Once we've determined that advection is occurring, we must figure out whether it is warm or cold air advection. If the isotherms approaching a specific location are warmer than the temperature in that location, then you have warm air advection. And if the isotherms approaching a specific location or area are colder than that location or area, you have cold air advection. So in the examples you see here, the solid black lines are our height contours, The dashed red lines are our isotherms, each labeled with its respective temperature in degrees Celsius, and the black arrows represent the direction of the flow. And our goal is to determine the type of advection ongoing between points A and B. In the left-hand example, we notice that the isotherms are decreasing in temperature as we go from point A to point B, meaning that there is warmer air at point A, and so the southerly or southwesterly flow is transporting warmer air from point A to point B, and therefore we have warm air advection. In the right-hand example, we notice that the isotherms are increasing in temperature as we go from point A to point B, meaning that there is colder air at point A, and so the northeasterly flow is transporting colder air from point A to point B, and therefore we have cold air advection. In general, in the United States, if you have flow with a southerly component that is advecting air into a region, that will tend to foster warm air advection because, of course, the air tends to be warmer the farther south you go, so that flow would be transporting warmer air into cooler air. The opposite is true for more northerly flow, which generally fosters cold air advection. In addition, low-level warm air advection tends to make the environment more unstable for convective development, and it also contributes to rising motion that can either prime the environment for convective initiation later on, or in rarer cases initiate storms on its own. Generally, these storms that are forced solely by warm air advection are elevated north of frontal boundaries, but in certain cases the low-level warm advection can initiate surface-based convection in the open warm sector in certain severe weather environments. So on our sample 850 millibar map, we notice here across the Midwest that we have strong advection ongoing. Tightly packed isotherms crossing the height contours, which are fairly tightly packed themselves, at a decently perpendicular angle. We have warmer air moving into a region of cooler air. We can look at our red values here, which are the 850 millibar temperatures in degrees Celsius, 11, 11, 11, mostly single digits up here, so we have warmer air moving into a region of cooler air. That signifies warm air advection. In contrast, across Oklahoma and North Texas, we have strong cold air advection ongoing. Tightly packed isotherms nearly perpendicular to the height contours, and we have colder air moving into warmer air. You see Amarillo is at 4 degrees, Oklahoma City 0 degrees, Dallas-Fort Worth at 10 degrees. So colder air moving into warmer air, that signifies cold air advection. Over here across Arizona, we have very minimal temperature advection of any kind ongoing, as the isotherms are generally parallel to the height contours. Another popular use of the 850 millibar map is to locate frontal boundaries, especially when they're difficult to find at the surface. If you recall, fronts don't just exist at the surface, they slope back into the cold air as you go up in the atmosphere, so they tend to show up well on the 850 millibar map. We're using the same concepts to find fronts as we are at the surface. We're looking for wind shifts, temperature and moisture gradients, etc. Also, isotherms are packed tightly on the cold side of frontal boundaries. So if we look across the southern plains into the southeast, we see a notable wind shift with a clear temperature gradient across the region. Single digits into the low double digits across the southern plains, transitioning to about the mid-teens across the southeast. We also notice that our isotherms are packed very tightly together across eastern Oklahoma into North Texas, and as we said, those tend to be packed on the cold side of frontal boundaries aloft. So we can fairly confidently draw in our frontal boundary somewhere in this vicinity here. Now, as we said, fronts slope back into the cold air as you go up in the atmosphere, so the location of the front at 850 millibars is often behind the location of the surface front. This is not always the case, especially in the plains where the cold front aloft often moves faster than the cold front at the surface. This can create some interesting things to watch for in severe weather setups. These fronts aloft can, number one, provide a mechanism for storm initiation, often within the open warm sector, which tends to yield more discrete storms, and number two, bifurcate the wind profiles across the warm sector between less favorable for tornadoes behind the front, due to generally more veered low-level flow, and more favorable along and ahead of the front. Take this example from March 31st, 2023, where we had dual high risks, one up in Iowa and Illinois and one down in Arkansas and Mississippi. In the northern mode, models indicated a clear leading cold front aloft, demarcated by the green dashed line on this graphic by Cameron Nixon. Notice how the photographs are much more large and looping along and ahead of the green line, whereas they are not quite as favorable for significant tornadoes between the main cold front, the dashed blue line, and the leading cold front aloft. On the same token, we can look for prefrontal troughs and confluence zones using the 850 millibar map, and a product I like to use to do so is the 850 millibar relative humidity product on the College of DuPage model site, an example of which you see here. This product features streamlines, which are these blue lines with the arrows on them, and they help you visualize the flow at the 850 millibar level, perhaps a little bit better than by just looking at wind barbs. Always look for little kinks in the streamlines in the open warm sector, as these can represent prefrontal troughs or confluence zones that can provide subtle forcing for discrete warm sector convection, and if the wind profiles favor tornadoes, these warm sector storms may have the best chance of producing them. The map you see here is not necessarily an example of a prefrontal trough scenario, but it does show how this product can help you identify areas of confluence. Here is a cold front as progged by the GFS model, and you can see how the streamlines clearly denote the area of confluence along the boundary. Finally, we can use the 850 millibar map to analyze low-level moisture. Depending on the source, upper air maps will list either dew point or dew point depression as that bottom left value on each upper air station plot. Standard upper air station plots, including those at 850 millibars, give the dew point depression, which is simply the difference between the temperature and the dew point. Some map sources, however, including the SPC upper air maps, an example of which you see here, give the actual dew point as that bottom left value. If you see negative numbers for those bottom left values on the station plots, you know you're dealing with actual dew point because, as we know, the dew point can never be greater than the temperature, and therefore the dew point depression can never be negative. Dew point depressions in the single digits, especially those of 5 degrees Celsius or less, indicate robust low-level moisture, which is favorable for severe weather. For example, again, the red values are temperature, and the green values in this case are actual dew point. And we can see down in Louisiana, Mississippi, Alabama that we have ample low-level moisture. 14 over 11 at Jackson, 14 over 11 at New Orleans, 13 over 12 at Birmingham, which yield dew point depressions well below that 5 degrees Celsius mark. And that indicates a juicy low-level environment there, whereas, say, in the desert Southwest, we have a very dry low-level environment. 13 over minus 17 at Tucson, which is a dew point depression of 30 degrees Celsius. One last note on the SPC 850 millibar maps, they do an isodrosotherm analysis beginning at dew points of 8 degrees Celsius every 2 degrees.
Remember to check out those links in the description below, and then watch another video.